Ah. Woo. Woo. Ah. Alrighty. 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 Alright. Ah, hello, everybody. I guess we should put on this boring music and begin our office hours. Much needed office hours, I would say, probably, for our algebra class. Um, so, to, I guess, I don't know how many people are actually here. Looks like not very many. So, meaning, I think a couple of you might be here. If I look in Discord, I see that 2 of you are online. I don't know if you're here though. If you're here, uh, class. Okay, one. Well, we meaning one is here. Who else is here? Yeah, you're here. um, is Sloth here? I don't know if Sloth is here. But okay, well, that's fine. So, AI, I am still climbing off the tree. Okay. Okay, be safe. Be safe. Interesting. I noticed something about your username. Looks like you've got oh, Crow is here. Crow, welcome, Crow. I noticed something, Sloth, about your username. It looks like you've got there the prime numbers. Is that right, Sloth? Crow, you're basically in the class at this point, but yeah, Sloth. For a very interesting reason. Sort of. Mathematicians don't consider the number 1 to be a prime number. And one good reason not to include 1 is that certain theorems statements become much cleaner. And you don't have to say, oh, except for the number 1, all this fact is true. You know, you don't have to put that clause in. That's one stupid reason why we don't consider 1 a prime. But we might at the end of the class, when we do ring theory, some basic ring theory, we'll learn what the true definition of a prime is. Very general definition. And you'll see that the number 1 kind of messes up that definition. So I'm waiting for my professor. All right, I'm here. I mean, this is office hours, you know, it's a different vibe. All right. Let's see. People are getting anxious, and you know. Okay. So, what do we want to talk about here? Maybe first I'll address something. If the students, which I see 2 of you are here, students, you have priority. Do you have a particular question that you want me to address or try to address? If you have a question, then put it on the Discord. I'm reading the Discord right now under General. You should ask it on Discord, and then like I'll stop everything and try to address that question. Because it's important as we move forward. The class gets pretty hard, I would say. It gets difficult conceptually. And so it's very important that you ask all your questions about, well, the topic at hand here is group theory. But group theory is a difficult subject. You shouldn't feel like, oh, I can't piece together an argument in a simple exercise argument immediately like I can in high school algebra. This is not your grandmother's algebra. So exactly, it's already difficult conceptually. Exactly. That's correct. That is a correct statement. But it's gonna just get more and more difficult. And it's just building on building on building. So you have to make sure you use me as much as you can. To speaking directly to a person is much higher bandwidth mode of learning than trying to do it on your own or just reading Wikipedia or something. And you can see when I make mistakes, you can see. When you see that, you'll understand that, okay, yeah, I guess it was hard for everybody. So, okay, so if there's no specific questions, and as they come to you, just make sure you ask them, class. If there are no specific questions, how about together, kind of, you on Discord or in chat and me, let's start exploring the alternating groups. Okay, so let's kind of do that. Let's just explore the alternating groups. All right. So why not start with n equals 2? Nah, why not? That's a reasonable number. Okay. So the alternating group, it's a subgroup of the symmetric group on n letters, n symbols, n things. And it consists of the even permutations. The permutations, here's one definition that we can work with. The permutations that keep the polynomial, the discriminant, the same. I'm going to write this polynomial as delta because that's what people usually write. Okay, delta, which is all the numbers I less than j, but like going up to 1, I mean going up to n and starting at 1, of xi minus xj. All the differences between variables, but don't do the other difference if you do the first difference in this expression. Hello, Tomas. Hello, or Tom. Okay, so let's try it. Let's try it. So n equals 2. The discriminant is a wonderful polynomial, and the question is, which swappings, which permutations of the symbols x1 and x2 keep this polynomial the same? Well, those permutations keeping delta the same. Oh, Gath! Hello, teacher's pet. Gath is today's teacher's pet. That's incredible. I mean, it's not. I mean, they're a great student, but they're also actually a great teacher. They teach organic chemistry, and I should do a shout out for Gath. Go check out Gath. That did not work. Check out Gath's emote at Gath's emotes. Gath's emote has its own Twitch. There we go. There we go. That's better. Oh boy, I am not a pro streamer. All right, awesome. So those permutations keeping this discriminant fixed. Okay, but this is clearly only the identity permut. I don't know how you write identity. And so that's why A2 is a silly example. A2 is just the identity subgroup. So the alternating groups will start getting more interesting when we look at n equals 3. So let's look at n equals 3. What is A3? Okay, so A3, it's the permutations of the three numbers which keep this discriminant polynomial the same. Maybe I should put a little subscript now, because it's degree 3 now, or the not degree, it's the third one. 1 minus 2, let's say 1 minus 3, and then 2 minus 3. Which keep this the same. Which preserve it. Which maintain it. Alright, so let's look at A3. What's in A3? Alright, I claim that any transposition is definitely not in A3. Okay, so here's a claim. Any transposition, which you'll know what that is if you've taken a look at your homework assignment for Monday. A transposition is just any permutation whose cycle notation involves only two of the elements, A, B. As a permutation, it just swaps two elements and keeps all the other elements the same. That's what a transposition looks like. Keeps everyone else the same as a permutation of the set. So any transposition will change delta 3. Okay, let's take a look at that. So for example, 1, 2. Right? It's actually easier to see that adjacent transpositions don't do much, but you know, you still have to like squint. Okay, look slowly at what happens here with 1, 2. Let's look. Our discriminant does the following. This factor, the first factor, when you apply the permutation 1, 2, x1 becomes x2 and x2 becomes x1. So this becomes exactly the opposite. This got a minus sign. This became the negative of the other. Good. Then x1 minus x3 becomes x2 minus x3, and then x2 minus x3 becomes x1 minus x3. So then what happens is that this one becomes x1. I don't know how to write. What's the best way to explain this now? But there were no more sign changes. None of the factors became negative, right? And so this negative, which is not the same. We did not preserve the discriminant. Okay? Similarly, same type of thing happens for 2, 3 and 1, 3. These transpositions. Oh, Sloth is typing. I'll wait. I eagerly anticipate your, I'm sure, wonderful question. Okay, so, or comment, whatever. All right, so these little transpositions, they will have the effect of changing the discriminant to minus the discriminant. All right, the net total minus sign changes will be an odd number. If you just right now, if you just try it empirically, okay? And for A3, you can just check them all, and you're gonna get these are each odd permutations. All right, it's confusing because these permutations, they involve two symbols. Each of them only involves two of the symbols, 1 and 2, 2 and 3, and 1 and 3. 2. Yet they are odd permutations. So don't get confused by odd meaning has to involve only an odd number of terms. That's not how it works. Okay? All right. So what's left in S3? What's left is permutations like 1, 2, and 3, and its inverse, which is 1, 3, and 2. These two are inverse permutations of each other. And of course, there's the identity. Okay, the identity is obviously even. By even, we mean identity obviously keeps the discriminant fixed. Awesome. How about 1, 2, and 3 though? 1, 2, and 3 takes our discriminant okay, I'm analyzing 1, 2, and 3. Takes our discriminant 2. So 1 goes to 2, 2 goes to 3. 1 goes to 2, 3 goes to 1. looks like we've picked up a minus sign, but hold on. 2 goes to 3, 3 goes to 1. We picked up 2 minus signs. Picked up 2 minus signs. So that's fantastic. This is even. All right. So that's an even permutation. And then 1, 3, 2 will also be an even permutation. So look, here's the principle. If one scrambling of the variables keeps a polynomial the same, and if one scrambling sigma keeps the polynomial the same and tau also does, then tau composed with sigma also does. Because you have this polynomial, expand it out. Brilliant. Look, I don't know how to expand this delta out. It's some horrible mess. What'll it be? So expand it. It'll be like, it'll have like x1 squared, x2, boom, this minus x1 squared, x3, okay, and then wow, it's just wow, plus da 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 da. Okay, big old polynomial. All right, I can't even do it anymore. I'm too old. Sloth, those are good questions. However, Sloth, that question is great. However, the ultimate answer is that there is no well-defined sign. Actually, I'll take that back. I will take that back, Sloth. Let me talk about, that's a good question. Let me talk about it afterwards. That's actually a great question. It's a good question. Let me try to address it afterwards. Okay. What else? Yeah. No, Sloth, great questions. We're gonna address those soon. Okay, so if you have this polynomial and you know that by doing this kind of one particular scrambling of the variables and collecting terms, it looks exactly the same, and then you do the other scrambling and it looks exactly the same, then if you do the first scrambling, then the second, well, after the first one, it was the same polynomial, and then the second one takes that polynomial and outputs the same polynomial. So the composition, if they both preserve the polynomial, will also preserve the polynomial. It'll keep the polynomial same. All right? So this is why preserving a polynomial will always yield a subgroup. A group of permutations that are fixed. A group of, a set of permutations that stay closed within the group operation. All right? And the same sort of, if you undo a scrambling that fixed the polynomial, then the resulting polynomial will still stay itself. Okay, so awesome. Okay, so now what do is so that means automatically this has to be even, because this one was even and the other one is like the square of the first one, or the inverse. This element has order 3. So here's your A3. A3 is identity. The cyclic shift, musical chairs, or whatever. And then the square of musical chairs, which is that element. Okay? 1 goes to 3, 3 goes to 2, and 2 goes to 1. So this is what A3 looks like concretely. All right? And notice it has 3 elements. All right. A4. Oh, actually first, let me deal with Sloth. Thank you, Sloth, for the question. The question is conceptual. It seems that we are only talking about the sign of a permutation, or the evenness and the oddness of a permutation. In the context, only in the context of a permutation group of Sn. But is there a notion of sign, I'm paraphrasing, or of an arbitrary element in a group, of an arbitrary group? Is there some intrinsic notion of sign? Okay. I was gonna say no. However, if you use the proof of Cayley-Hamilton, you will notice that the group G can be placed as a subgroup. Remember, the hook right arrow is injection. There's a injective homomorphism, a way of just placing the group faithfully within. No collapsing and then placing. There's no kernel to this. There's an injective map. There's no 2 points getting loss of information. There's a way of putting this inside of a permutation group. And in permutation groups, you have this intrinsic notion of sign. So here, there is a notion of sign. And what we had this map T, so that you should go review. So actually Sloth, yeah, elements do have a sign, given by what is the corresponding sign of the corresponding permutation that this element produces. So it's yeah. Oh, thank you, Kappa. Thank you. So this is Cayley's. Oh, did I say Hamilton? Cayley's theorem. Yeah, Cayley's theorem. Thank you. Okay, so that's interesting. I never really thought about that. But yeah, I guess elements do have a sign in a finite group. That's cool. You can inherit it from the permutation action of the group on itself. Let's say it fancy. We're going to use the word action next week. I'm going to introduce the concept of an action. And so yeah, I'll just say it right now. Oh, wait. Are they all just shifts? Wait a second. Oh, but Kappa. They might not all be shifts. Yeah, they might not all be shifts. I think what you're confusing, Kappa, is that these permutations don't have any fixed points. That's correct. So let's talk about that. Some permutations have fixed points. For example, 1, 2, 3 as an element in S4 that has a point 4 that's fixed under the permutation. So Kappa, all of the non-trivial elements in the group G, they map to permutations which don't have a fixed point. This is because if G times an element, or if H times G equals H, then G is the identity element. And I'm saying every non-identity element will not have, as a permutation, the corresponding permutation of the elements in G will not have any fixed points. However, you can have permutations that have no fixed points. I have to go to a bigger group. This permutation has no fixed points, but is odd. But this is an odd permutation, kappa. All right? So I don't, so kappa, it's not clear to me that they are just shifts. Cyclic shifts. Well, hold on, let me think about it. No. It's not clear that they're not necessarily always shifts. For example, kappa. For example, kappa. What if an element in G had order 2? Just think about this case, kappa. Then, I don't know what you mean by shift. I don't know what you mean by shift, but I'm imagining you mean this. Here are the elements, and then you just shift them over 1. Is that what you're thinking? Yeah. It can't be that, because G squared would be identity, and so whatever this permutation is, when you do it twice, you get the identity permutation. So shifting once and then twice doesn't get you the identity if you have 10 billion dots. Kappa, is this starting to, do you see why I'm concerned with your initial answer? But I do understand what you're saying. The permutations don't have fixed points. So that's something to think about. So Kappa's question, class, still stands. Is it still the case that G always lands in the alternating group? Is the image of G, here's a curiosity, I think it's not true, but here's a curiosity, is the image of T contained in the alternating group? The group of even permutations. A good question. Like kappa, this shift, just one, shifting by 1, right? Shifting by 1? Yeah, that can't be what every single element of the group outputs in all situations, because when you take an element of order 2, that would mean that whatever it's doing, it can't be a simple shift, because you can't do a simple shift twice and get back the same exact ordering. Some of them would still be such that G squared equals identity. G squared equals identity. Not G squared equals G. Yeah. Yeah, so I think we just have to try some examples to see if we can shoot it down right away. But yeah, we should file this. We should file this one away. It's a good question. Okay. All right. Does the sign of a permutation have any actualization in some concrete group like D3, dihedral group or tetrahedron, if this actually exists? Okay, Sloth has another question. Great question. I will give preference to the questions of my students over the thing that I wanted to just When there are no questions, I'll go back to my exploration of AN. Okay, Sloth asks, is there a notion of sign in, let's just say this is what you asked, Sloth, in D3? Yes, there is. Okay, there is one. When you look at D3 in a particular way. Okay? Let's talk about this. There is a homomorphism. There's a very simple homomorphism. I'm going to call it V from the dihedral group into injective. It's an injective homomorphism to Sn. What is the name of this homomorphism? I gave it the name V, but that doesn't tell you what it does. You have to immediately tell me, what does V do to an element? V of a symmetry. Let's call the symmetry sigma equals the permutation with a U, the permutation that sigma induces on the vertices of the n-gon. Every symmetry of the n-gon, the polygon, label the corners as 1, 2, 3, 4, n. Okay? Every single symmetry is going to do a permutation on those vertices. And there's no symmetry which keeps those permutations all fixed. That I just checked that the kernel was trivial. Okay? And so Dn injects, there's a group homomorphism of Dn into Sn. And so you can inherit the notion of sign from Sn to Dn. Sloth, is this making sense? Oh, actually, yeah, AI, ITA, you're right. Those two problems are really close. So if you have a way of like doing one without two, or two without one, or the other way, great. The way I do it, in my mind, I go from 1 to 2 for some reason. I deduce 2 from 1. But there are many ways to prove those two statements. ITA. So that's fine. As long as you're not doing something circular, as long as you're not doing a circular reasoning, great. All power to you. Awesome. Yes, there are actually many ways of doing many of these permutation group type proofs. Okay, facts about permutation groups. There's very ingenious quick ways of doing things. There's like slow induction ways of proving things. Yeah. It's a fun zone. Okay, so Sloth. Okay, good. Yes. So in other words, symmetries of the n-gon, they inherit the notion of sign from Sn. They can inherit it. And now I'll tell you what it is. Let me tell you what it is in pictures. Okay? Here's the sign. What it means geometrically in this context of Dn. And Dn is inheriting the notion of sign from Sn via the vertex homomorphism. Fancy. Look at all this fancy stuff we're saying. It's not. The idea is very simple. Oh, you have a symmetry of the n-gon? Focus on what it did to the vertices. You get a little permutation. Okay. So, the symmetries which don't flip the plane over, the piece of paper over, are even. And the symmetries that do require flipping the symmetries which do flip okay? But like, why did I say it like this? Because actually in your mind, whenever you have a notion of sign for operations being done on Rn, like R2, like the plane, then you'll see a notion of sign in that context too. And what fundamentally is happening is that those transformations which are even or positive 1 sign, plus 1 sign, even or odd, minus 1 sign. The ones that have plus 1 sign, they keep clockwise. So they keep all the clocks, the direction of clocks. Before you do the transformation of space, all clocks went a particular way. And then you do the transformation and suddenly the clocks start going the other way. That is the hallmark of whether the transformation had a positive sign, if it keeps clocks the same way, or if it had a negative sign. If clocks start going the wrong way, that's a sort of more geometric incarnation of this concept of sign. It's a geometric way of thinking about sign in the context of transformations of Rn, or of space, of higher dimensional space included. Okay, that's orientation preserving versus orientation non-preserving changes to space, or permutations of space, so to speak. Okay, so all right. So now, let me go back. Now that so Sloth, keep your questions coming. Try to keep. Yes, AI. Yes, AI, and on the YouTube, it'll stay up on YouTube as well. Absolutely. You leave whenever you have to. Okay. Thanks for coming. Thanks for asking questions. Okay. So, all right. So let me go back to my little story. Oh, Kappa has some progress. Did you do an example and did you find an odd one? Maybe D4. No, D5. No, D7. D7. No. No. Okay, so Kappa is saying okay, look at D3 going to Kaylee permutations of D3. Okay, identity is even. Reflection, good, is an odd one. Okay, they're saying that F goes to an odd thing. Okay, so let's take a look at this. So let's list D3. Identity F, rotate once by 120. Rotate twice by 120. And then F times rotate 120 and F times rotate 240. Okay, so here's our elements. You just think of them as 1, 2, 3, 4, 5, 6. And now what does how does this shift these elements around? What permutation does translation by F do? Okay, Kappa, I'm going to try to do this. It's going to do this. So identity becomes F. F becomes identity. Okay. I can use cycle notation here. Oh, okay. Okay, is better? Okay. So identity becomes F. And F becomes identity. Have I done it right so far, Kappa? Good. Now, R120 becomes... actually, here, just do this. I just cheated a little bit. Okay. Okay. Wait, it's a product of 3 cycles. Hold on. Oh, it's a product of 3 2 cycles. Oh, I get it. I get it. I get it. Yeah. 100%. 100%. I agree. There you go. There you go. Yeah. Yeah. So this, look, it's like 1, 2, 3, 4, 5, 6. That's the permutation that multiplication by F on the right does to these 6 symbols. And I'm really glad you went down this, Kappa, because now you see, my students can see how the Cayley proof goes. You just view the group as a bunch of symbols, and then multiplication by an element, let's say on the right, will permute these symbols around, and I just wrote that permutation for multiplication by F. So this is what is T sub F as a permutation? So thank you, Kappa. This was very instructive. And notice we have an odd, this is, oh, so class, I'm getting there. I'm getting there terribly with my slow pace. I'm getting there. But class, we will learn, probably not today, but on Monday, we will learn that this is an odd permutation. Actually, we can do it just by writing the discriminant and doing it. So check, class. This is odd. This is not an element in A6. It's an odd element. It will change the discriminant expression to its negative, unfortunately. Or, I don't know, interestingly. So there you go. Kappa has opened the door. Indeed, some elements in the group are even and some are odd. And very cool. Very cool. I never thought about this. So that's really interesting. Sloth, there you go. There you go. In possibly the first, maybe this might be the first example. Kappa will know, but Kappa, I don't know if you checked all the smaller groups, but maybe this is the first example. I'm not sure. Actually, hold on. Actually, Zmod 4Z. Zmod 4Z might give you a simpler example. Yeah, I think Zmod 4Z. Kappa, go find an example in Zmod 4Z. Great. Okay. But only after you showed me this example did there's a click that actually maybe Zmod 4Z would give you a better one. An earlier one, sorry, not better. Okay. Okay, A4. Let's go explore A4. Now the music is much much more. Wow, this is a jammer. Okay, A4. This is a subgroup of S4. We're gonna find A4 in two. We're gonna sort of first by hand write out the elements of A4. Okay, what are the elements in A4? I'm gonna tell you them. You'll have identity, of course, and then you will have every 3 cycle. Okay, you'll get those, but there's more. There's more. You get these kinds of elements, and then you get these 2 plus 2 elements. 2 plus 2s. Okay, now remember, I'm just claiming this. What you have to check is that all of these indeed keep the discriminant expression the same. All right? Because right now, that's the only way I've shown you how to tell whether a permutation is even or odd. I promised you I would tell you some secret, top secret information eventually, but right now, to stay consistent, go and check that these, just sample a couple. Convince yourself. By the way, notice how many elements this group has. It has 12 elements. Okay. And you might ask, like, how am I supposed to like think about these groups? Well, I mean, the silly answer is, do you know how to multiply 2 permutations? Let me do an example of that. Like, what is 1, 2, 3 times? I'll write a dot to indicate times, because when you're multiplying with cycle notation, sometimes if you only use juxtaposition, it can get confusing, because when are you writing it as the little cycles down? And okay, so I'm gonna just write dot every time I mean times in the permutation group. So let's do 1, 2, 3 times like 1, 2, 4. It equals? Okay, so you just start, you ask, where does 1 end up? 1 goes to 2, and then, so this is then 2 went to 4. So 1 went to 4. All right. Let me use some cool technology I learned about. It's called a laser pointer. Okay, so 1 goes to 4. Where does 4 go? 4 goes to itself here. Then 4 goes to 1. So 4 went back to 1. And so I can complete this cycle. Start the next cycle. Where does 2 go? Okay, 2 will end up. Isn't this cool how I did that? It's really cool. 2 goes to 3 first. Then 3 stays itself because it's not involved in that cycle. So 2 went to 3. Where does 3 go? Well, 3 has no choice. 3 has to go back to 2. You can't, the cycle has to end there. All right, so look at that. You can multiply 2 of these like 3 cycles. This is a 3 cycle. Because it's a cycle that has 3 things in it. It's a good naming system. You can multiply 2 3 cycles, and you can end up with one of these 2 plus 2s. In this case, it's 1 4 times 2 3 cycle notation. All right. So you might, if you thought initially that maybe those like 3 cycles form a little subgroup, including the identity, you'd be wrong. You do have to add, you sort of have to, like, if you include the 3 cycles, you're gonna have to include these like 2 plus 2s as well. But here, actually, here's something cool. If you multiply 2 of these, multiply these, or like these 2, or like these 2, or these 2. Multiply the 2 plus 2s, you'll stay within 2 plus 2 world and include the identity. Always include the identity. So identity, so it's curious. Identity plus the 2 plus 2s. This is a subgroup. Interesting. So A4 has certain subgroups in it, like a size 4 subgroup. It has 12 elements. It's got a size 4 thing in it. Okay, great. So what do I do now? Oh yeah, that's right. So what I wanted to show you next is where A4 can be found in nature. A4 can actually be found in nature. All right, A4 has a incarnation as the symmetries of a tetrahedron. As incarnation So just like dihedral groups were symmetries of a perfect n-gon, by symmetries we mean like rotations and flips. If we start with a tetrahedron, which by the way, this is not a tetrahedron because it has a square base. But let me try to draw one for you. That's right, Kappa, absolutely. So let me try to draw one for you, draw a tetrahedron. That's pretty good. But you have to imagine like every side is the same. It's like an equilateral triangle, all 4 sides, right? Now, why should we try to imagine this? I mean, you should try to imagine this, and then we're going to like do all the rotational symmetries of this thing. And the claim is the group of rotational symmetries of the tetrahedron is isomorphic to A4 via the vertex map, just like it was for the dihedral group. No, sorry. Just like there's a vertex homomorphism from Dn to Sn, there's a vertex homomorphism from tetrahedron symmetry group to S4, and the image is A4. So let's talk about this. Let's go. Okay, let's go. All right, let's go. Yes, Kappa, I agree with you. It's the size of the, if it's 4 elements, yeah, I think you know what you're doing. Yes, exactly. So Z mod 4Z. Okay, so here we go. We're gonna go and check out the Oh god, how do I do this again? There it is. Alright, folks. Let's go check out the symmetries of a tetrahedron real fast. Oh my lord! Check out this awesome place! Isn't this incredible? Alright. Exclamation point attend in the chat. We'll probably get you here. Are you guys here? Oh, there you go. Here's... Hello, Stuck. How are you? Hi, Sloth. Hello? Hello. This person made this place. This person made this whole place. That's right. That's right. Well, whoa. Interesting. Hold on, hold on. Well, that's cool. Look at this. That's really cool. Hi, Tropical. Hi, Donkers. Calc Math. Welcome. All right, so this is abstract algebra's world. Interesting theme. But look what we've got here, folks. Look what we've got here for you. We've got a tetrahedron. Ready-made, perfect, all sides are equilateral triangles. This is one of the 5 Platonic solids. Okay? One of the 5 most symmetric shapes in the universe. In R3. It's one of... Hello? My pen not working? Hold on. Hold on. Let me try to write real fast. Oh, I think I know what I did. Okay. One of... Wait, what? Hold on, hold on. I'm trying to pair my pen. One of 5 Platonic solids. Tetrahedron. We will eventually go study all 5 of them. What a treat. And they will be available here on this in my third eye, in right here in this safe place of mathematics. Okay, so here we go. Let's check out some of the symmetries of this tetrahedron. Now, how does this work? It's right here under the polyhedra section, tetrahedron. And notice we have one option. We have one option. We are given one option. Okay, awesome. So I'm going to choose tetrahedron for today. And the naming system is interesting. I believe I understand it. Let's see why don't we just try something, okay? Let's look at R11. Aha! Rotation around the red dot in the clockwise direction? That's interesting choice. Clockwise. Let's do that. Clockwise rotation. Righty-tighty. That's why it's R. I see. Righty-tighty. It's one rotation. One sort of 120 degrees, so to speak. I mean, exactly that. Okay, let's do what? Let's look at R12, folks. I wonder what R12 is. Pay attention, look carefully. Maybe I should change my position? No. Okay, let's just look at it. Ready? Pay attention. I'm gonna click it. 1, 2, 3, click. Boom. It is 2 rotations. It is R11 squared. That's what R12 is in this notation. Okay? All right. So that's cool. There were some other options here. What the heck is R sub A? Let's check out R sub A, but maybe I should go into a better position here. Let's look from this angle. Okay. What the heck is R sub GD zag? Okay. Let's do this. RA. RA. Ready? RA. Ready? Whoa. This one is confusing. But let me look at it from another direction. Let's see if we look at it from here, what it looks like. Okay, what I want you to focus on, folks, is, you see where my cursor is? Focus on this midpoint here. Focus on this midpoint. And then the opposite midpoint of this edge. This edge midpoint and this edge midpoint. Focus on these. This point here and this point. Okay, focus on those two. And I'm going to do this RA symmetry. Wow. Look carefully. Focus right here. Let your concentration center right here. Midpoint of this side. Incredible. Okay, so let's go back to learning. I mean, we were learning this whole time, but let's get out of here. Let's X out of this. Okay. Okay. So, yes, I see that people have a question. Okay. You might not believe in that symmetry right now. Wait, is it in the same spot that it was? Yes, exactly. Those 2 points were fixed points. Okay, so students, what I'm going to try to explain to you is that that symmetry is real. It's not fake news. Okay? So I'm going to try to explain that. Let's go talk about that funny symmetry. Okay, so you all believe in the rotation around a corner symmetries. There's a bunch of those. In fact, if you go and count how many of those symmetries there are, class, you need to do this, you will find that each corner contributes 2 rotations. Rotate 120, righty-tighty, and then let's say rotate 120 the other way, lefty-loosey. Or lefty-loosey is righty-tighty squared. Okay, so each corner contributes 2 of these rotation things. And in your mind, you need to start trying to align those with the little 3 cycles. That accounts for 8 symmetries of the tetrahedron. Identity is always a symmetry, meaning don't touch the thing. Okay, but these funny 2 plus 2 things, they can be seen as they manifest as symmetries of this goddamn shape. All right, so I'm going to try to convince you that they are actually symmetries. Okay, how do I do this? What you do is you take your tetrahedron and choose 2 opposite edges. And in the opposite edges, color them right in the middle, and then stab a line through the 2 dots. Stab an axis. I'm really bad at drawing, but right through the middle of the 2, stab an axis, and then here's the thing. The tetrahedron is kind of symmetrically positioned around this axis. In fact, if you look through this axis, you will basically see like a square. Let's go check that out. Let me go confirm that. Let's go back. Let's go back, folks. Let's see. What does the tetrahedron look like when I look down one of these axes. Incredible. This is an incredible question that I just asked. All right, let's see. Okay, where is this axis? Okay, here it is. Okay, let me align myself, my spaceship. Okay, you don't see a square, you see some kind of rhombus. Does everyone see this? See this picture? I'm looking right down that mysterious axis. That's what I'm doing. And now I guess I should try looking at RA again. Whoa! Now you believe in it. Now you believe in it. Now you believe it. It's just that when you look at it from the side, you don't believe it anymore. But from that other view, it's clear that there should be a symmetry because you get a rhombus when you look at the thing from that axis point of view. All right. Okay. So that's the... Okay, do you guys want attention? Okay, here you go. Sloth, you get attention. Stuck, you get attention. Welcome. Thanks for showing up. Boring Professor Servant, you get attention. All right, good. All right. Let's... Oh, wow. Look at that. Look at that. That was incredible. Oh, Tropical Geek. Wow. Look at that. Wow. Incredible. This is a cool place. It's like a stadium. It's like a rock stadium. It's incredible. Hey, look at that. All right. All right, let's get out of here, folks. Okay. Okay. All right, so here's how I tie up this tetrahedron group to A4. So here's the grand claim. And class, you should verify this. Here's a claim. Label the corners of the tetrahedron 1, 2, 3, and 4. Just put symbols next to the corners. And now define a homomorphism V called vertex from the symmetries rotational symmetries of the tetrahedron to S4 by the rule send a symmetry goes to the permutation it induces on the vertices. Every symmetry will permute the vertices. That's the output element in S4. Define this homomorphism and then check that this homomorphism onto A4. So, curiously, the alternating group in A4, in S4, has a visual incarnation. That's really cool. Okay? Not all subgroups of Sn have a nice incarnation as the symmetries of a really gorgeous simple shape. Only some of the smaller groups have such interpretations, and A4 has such an interpretation. And that's what I wanted to show you when it comes to A4, alternating group. Punchline for just getting a handle on alternating groups. This alternating group has 12 elements. Notice that 12 is exactly half S4 has 24 elements. This has exactly half. All right. So next time, probably on Monday, we'll keep talking about AN, and I will prove the following fact for you on Monday. It's a neat, simple proof, but we will prove the following thing for Monday. IOU Monday. In the concrete part, where I don't do conceptual thing, I do concrete, hands-on, particular group stuff, or I try to do that in my 45 minutes. So IOU on Monday, the true definition of even versus odd. I gave you a working one, which is totally fine. But this other one that I want to show you, this other way of classifying permutations as even and odd, is way more useful in practice. Okay, so and what this is so it's the following mathematics that I need to show you. Number one, every permutation can be written as a product of some number R. No, let me not specify. Some number of transpositions. That's your homework exercise, I know. But you're going to take this observation, and then I'm going to add a second thing. If you write the same permutation as a product of transpositions in two different ways, For example, if you have one transposition times a second, times means compose in the group law, not, I'm not saying you have an element of cycle type 2, 2, 2, 2. No, I'm saying you have a 2 cycle times another 2 cycle times. If you can write the same element in two ways, then it's not the case that the number of factors is the same. That dream is not true. That's not a true dream. This K and this R, these don't have to be the same. But they're either both odd or they're both even. They have the same parity. And if you can write it, so therefore, it makes sense to talk about a permutation being even. What it means is, when you try to write it as a product of transpositions, you have to use an even number of transpositions. And a permutation is odd if, when you try to factor it as a product of transpositions, you must use an odd number. There's no particular number that that a permutation gets factored into as a product of transpositions, but the total evenness and oddness of the number of factors is consistent. And that's the conspiracy that I have to explain to you. This is the true conspiracy underlying the concept of even and odd. And it's where the words even and odd came from. So I'll prove this invariance of parity property next time. It's really fun. Okay, so Tropical Geek has redeemed Shungite, as they typically do. So here you go. 3 Shungite circles so that you're protected for the rest of your day. There's that. But folks, I mean, this is really fun. I hope it was fun for you. And there are 15 people here, but there should only be 2. There's only 2 people in the class. So whatever you're getting out of it, I'm glad you're getting something. I hope you enjoyed the third eye, the beauty of the third eye. As you can see, it's under development and it's developing awesomely. Incredible. That's my little brother just doing it for you guys. That's it. That's literally just volunteer. So Kappa, great contributions. Awesome discussion. Interesting examples. Thank you. Yeah, Sloth, wonderful question you asked. That's a wonderful question. Yeah. So elements of a group do have even and oddness. Very cool. I have beautiful handwriting. Thank you. I hope my explanations are somewhat beautiful too, but I'll settle for handwriting compliments. Thank you. That's what I went for. That's what I went to grad school for. So thank you. I went there. I did a lot of the tracing. You know that from kindergarten when they make you do this. Grad school was like this. Like, look, notice how good I am at this. See how fast? Look at the pace. Hey, Stuk, look at the pace. No, you know, not anyone can do this. This only happens because I went to grad school. Okay? Yeah. All right. Yeah, the dotted lines. Exactly. Exactly. But I don't need them anymore. I don't need the dotted lines. I can just go straight to the letters. And that's because of because of grad school. So, okay. Anyway, this is getting dumb. All right, let's go. I gotta go, folks. I just gotta go. Thank you all for showing up. It was great. It was fun. Lots of hearts in the chat. Students, thanks for coming. Yeah, absolutely. We'll have this algebra office hour every week, Friday at 5 like this. The thing is I can engage with better, fancier, harder questions. I can't do that during my 45-minute lectures. So if I come off as like, okay, yeah, get that out. That's a good question. All right, stop. It's because I have to. But here I can just chill and engage with the chat, like with Kappa, so on. Okay, so see you all on Monday, and students, see you all on Monday. So thanks for coming. I'll upload to YouTube. Okay, good. All right. So with that, have a good weekend. Go and play around. Go see if you can write down some elements in A5, the 5th alternating group. Yeah, have fun. Have fun with that. I'll see you guys on Monday. Bye-bye. All right, I gotta press end stream.